This is my pleasure to welcome Hanuman Singh to our to UW, and he's a professor at Northeastern University. He received his PhD from the MIT program in 1995. He's been very phenomenal in terms of in field robotics. He has participated in around 50 expeditions and across all the world's oceans to support marine geology, marine biology, polar studies, coral reef ecology. It's phenomenal. So with no further delay, I'd love to basically listen to what Hanu has to say.
All right, thank you so much, Shyam. Hopefully you guys can hear me. The wonderful thing about Zoom is that I can give the start from my study. Having said that, because of that informal nature, it's sometimes hard to interact with you guys. So, don't hesitate. I will not take it amiss. You can come in with questions at any time. You guys don't know me. If you were in my class, you would know that if you don't ask me questions, I'm going to ask you questions, and we're going to do that anyway, right? And all right. And so here's what I thought I'd do today. I thought I'd talk a little bit about field robotics, and think about where we've come from, where we're going, and also give it from a little. I'm getting to be old. Okay, I'm going to give it from a slightly historical perspective about what's been happening and how things have been moving. So, here's my title slide. There's the Titanic. The Titanic sank. We should get over it. We'll talk about it a little bit, and we'll go from there. But basically, I'm going to talk about what are known as autonomous underwater vehicles, which is vehicles which are autonomous and go explore the deep ocean. And then I'm going to talk a little bit about certain other aspects of the work that we do. So even though we build these robots and use them, nobody gets tenure for building a robot, unfortunately, right? And so, how did all this work that we've been doing, how does it fall into the theory of robotics? And, I've been working in SLAM for a long time, so I'm going to try and knit those two things together, okay? And then because this is a student colloquium, I'm also going to try and, pose some thoughts and some questions about how we want to do research and what research means to all of us. Okay, so here's some vehicles that work underwater. On the top left is something called Alvin. It's a manned submersible. It's one of the largest titanium spheres ever built in the world. It's hard to tell you the scale on this thing, but that gray thing you see, the hatch on the top opens, 3 people sit in it, and it dives to the bottom of the ocean for a day. Okay. On the right-hand side on the top is what's known as an ROV. It is a robot which has a fiber optic tether going to a ship, and that includes electric cables, so you can power it from the ship, and you have 3 fibers. So you have a lot of data you can get back in real time. And I'm not actually going to talk about those 2 vehicles, though we worked a lot with them. I'm going to focus on autonomous vehicles. And autonomous vehicles are, hey, we've got the sensors, we've got the vehicle, everything's in one package. We drop it over the side, we pray, and hopefully it goes out, does its thing, and comes back, right? And that brings me to the first law of field robotics, okay? The first law of field robotics says that the number of deployments you have should equal the number of recoveries, okay? And that's one of those, fundamental laws. If you don't follow that law, you're having a really bad day. These vehicles cost a reasonable chunk of change, and then there's the mental cost associated with losing a vehicle, okay? And, one of the interesting things that happened is we built this vehicle, we built it for our own research. Every time, a young professor comes along, they decide, hey, let's build a new robot, okay? Because it's cool, because we want to, and that's why we got into this whole field anyway, right? And their mentor, as in my case too, says, don't do it, Hanu. You won't get tenure for building a robot. It'll take a lot of time. What are you gonna do with it, okay? And the mentors are right, okay? Now that I'm a mentor to the young folks, I say the same thing to them, okay? But I never listen to them. So we built a robot. It worked really well. We built a second one for one of my students who was going off to Australia. We built a third, we built a fourth. And today they're all over, okay? You may have seen one, that, the one on the top left is one that Stefan Williams runs out of the Australian Center for Field Robotics. Right here in Seattle is the home of another one called Lucille, which is run by NOAA, by the Northwest Fisheries Science Center. And then below is one run by the Taiwanese. There's others all over the place. Okay, and now, let's take a step back and think about what are the real hard problems underwater. And the biggest problem underwater is that there's a very strong and nonlinear attenuation of the electromagnetic spectrum. Okay, so everything that you can do on land, you basically have to get rid of. You have no GPS. Okay, RF doesn't go very far. You have no Wi-Fi. Okay, so everything you do is with acoustics. Okay, and so you're trying to do your navigation with acoustics. You're trying to do your communications with acoustics. So our bandwidth, for instance, is often measured in bits, in baud. Okay, we're still back in the day. And not only that, it's not just that it's low bandwidth, it's also that it's low bandwidth and it's not predictable. So you might get a little burst of data right through, but then you might get nothing for a while. So we have to deal with that, all those kinds of issues, right? And I'm not really going to talk about them other than to say that, it's a very challenging environment to work in, right? Now, when we think about images, we have the same problem, right? It's part of the electromagnetic spectrum. And, because sunlight doesn't travel very far, you have to bring your own lights with you. And all of you who've built robots, right, you realize that, the overall power budget on a robot may be, of the order of 100 watts or 300 watts, depending on the size, but the lights themselves are taking half of that, right? If you've got a 50-watt light and you've got a 100-watt robot, it's hurting you a lot. And underwater, what happens is, if you look at most pictures underwater that are taken from slight distance, you'll see that they're either green or blue, And what's happening is the reds are getting attenuated way faster than the greens and blues, even over distances of 3 to 5 meters, okay? And so what that means is you're not getting the true color that's happening. Then if you get your lighting, you've got the non-uniform effects of lighting that go on. And then if you try and move back a little bit, say from 3 meters away to 10 meters away, you have this concept called backscatter, okay? And so what backscatter is there are these small suspended impurities in the water, even in the cleanest water. And it's like driving in fog. If you turn on your headlights, all the energy gets backscattered at you. So these are all challenging things. So what you see here is, if you look at the bottom left, you see an image in green, okay? And on the right, you see, on the extreme right, you see that same image color corrected. And I'm going to talk about that. And then what's interesting is, because you're carrying your own lights with you, your lights are casting shadows which move, okay? And so you look at that last column, there are 2 images. I've even done the favor of color correcting them for you. And, every time I show the slide, I have to look at it twice. Usually when you see pictures with, 30, 40% overlap, it's easy to figure out where the overlap is, okay? So I want you to think about where the overlap is in this image, all right? And I'm going to leave it as a homework problem, okay? And, for those of you who don't know me, a homework problem means something that I'm not going to tell you the answer to, okay? So let's move on a little bit. And one of the first things we did is, and this is the work of Ali John, who was then a postdoc, and of course now he's a scientist in his own right, is we worked on color correction underwater, okay? And, we've got all these theorems and we've got all this theory. And what we can do is, as long as we have the dynamic range, we can accentuate the reds so that they match the greens and the blue. And if we have one point in that spectrum, which, and there's different ways of getting it, then we can get what's called true color. And what we define as true color is, if you drained the oceans, you looked at it with, sunlight, and you had a nice white spectrum on your camera, then this is what you would see. So a lot of the images I'm going to show you are going to be color corrected like this, okay? 99.9% of the images you see in the real world from the underwater world are not color corrected. They don't have the dynamic range. They suffer from this, and that makes the problem even harder, okay? Now, so let's talk about, what are the kinds of problems we really want to work on, okay? And, this is the one thing that I would like to tell all of you who are listening. Work on big problems. You can do a really nice job on a small problem, but it'll remain a small problem. If you do a halfway decent job on a really big problem, that's going to make a big difference, okay? So this was, one of my students, I chatted with him. I said, we're going to call your thesis is going to be called one fish, two fish, red fish, blue fish. We're going to go out, count all the fish in the ocean, and we're going to classify them to the species level. Okay. And that's, and how did that come to be? Well, one of the things that happened once is we were showing those color correction slides. I was at a conference, and this woman came up to me afterwards and said, "Hey, I really like that. Here's my card. We should talk." And her name was Liz Clark. This was in 2000, and I want to say 2003. And she is a program manager with the fisheries program at the Northwest Fisheries Science Center right here in Seattle. And she said, I'm very interested in looking at fish in rocky habitats. We can't use trawls. We can't use the standard fishing gear we use to, to go out and figure out how many fish there are. Can we use your vehicle to go out, take pictures of the seafloor, and get a count of how many fish there are? So the idea is basically this, right? And there was somebody wrote a science paper about this. They said, hey, we have an AUV. It goes out, and guess what? We can see pictures of the bottom. We can see fish on them. So we don't need to catch fish to count them anymore, which is the classical way of doing it. Why don't we just go out and do lots and lots of surveys and see if we can find count how many fish there are. And there's a long story there, and I'm going to tell you parts of it. Okay. And part of it was we started working with Liz. We went out with her, on the RV Thompson, which is the ship that the University of Seattle runs, University of Washington runs out of Seattle, multiple times. She really liked the work we were doing. And after 3 years, she said, you know what, we now need to transition this to a real tool. And when she said that, I shrunk back because, I was young at that point, and I wanted to remain married, and I didn't have time to go to sea 3 or 4 months a year just with Liz's cruise. Okay, and so what we did is we built a copy of our vehicle, and we gave it to Liz, and now she and her group run it. Okay, and what was interesting is, when you think about it, okay, it's just a robot, it's just taking pictures. Yes, it's a hard problem, but where's the theory? What are the harder theoretical problems that come out of this? Okay, and as soon as you start looking at some of this real data, it becomes really interesting. Okay, so one of the interesting issues is this is, again, a color corrected image, and you guys can see the skate in there, right? Everybody see the skate in there? Yes? So Sean, I'm going to pick on you. You are my, can you see the skate in there?
Yeah, I think so.
Right in the center. Yep. Do you see the second one?
No.
Okay, if you look right above, I don't know if you can see my cursor. If you look right above there, there's another one, which is kind of buried in the sand.
Yeah.
Okay, so, and you can imagine if this was not color corrected, you wouldn't see either one of them. I should actually put that original image up there too. But the point is, look, it's hard to see these animals because they're hiding, not from us, but from their predators, or they're the predator, trying to make a jump at somebody else. So suddenly there was this really cool idea about, camouflage. What can we do with camouflage? Okay. And so let me show you this clip. It's called Wow. Hold on. It's called Wow. So it better be good. Some of you may have seen it. Okay. It's taken by my collaborator, Roger Hanlon. I'm just going to play it. That was an octopus, okay? And, they are absolutely amazing. It was hiding there, and Roger knew it was hiding there and happened to see it. I'm gonna keep playing this. It's gonna play in slow motion reverse, and you wanna see what that really looks like. Okay, so that thing is absolutely unbelievable, right? I showed this once I shared this someplace, and they said, that's such a cool simulation. I'm like, no, it's not a simulation, it's real, okay? And then there are some other interesting things about this reality, okay, which is that octopus are colorblind, okay? And they can, change the pigments on their skin and do this stuff. And it's a very interesting problem in camouflage, okay? And what's even more interesting is that, let me show you the next slide. Okay, now, here are 4 images, okay? And we have octopuses, octopi, yes, octopi, hidden in each of those 4 images, okay? So Shyam, you're on, okay? I don't know who else to pick on. So I'm gonna, with my cursor, I'm going to point out where the first one is. You can see its eyes right here, and it's sitting right here. Okay, do you see it?
Yep.
Okay, now your turn. Where is it in the second image?
I think it's in the middle next to that fish.
Middle next to that fish, right here?
Yeah, a little bit higher than that.
No, sorry.
No,
I'm going to point it out to you. Okay, then
right
this,
oh.
Is it right?
Okay, here it is right here. You guys see it?
Yep.
Okay, and what's interesting to note is, unlike the skate, it's not putting sand over it, okay? It seems to understand that there's a family of textures in the background. It can't match any one of them, but it can stay in that family of textures, and that's how it's doing camouflage, which is kind of amazing, right? Okay.
So this is like a pretty hard problem, right? Like, how do you get the ground truth? And
So that's a really good question. Okay, hold that thought. And actually, no, I'm going to give an editorialize on that thought, especially for the students. So whenever I get these problems, sometimes I get these problems, which I look at that and I say, there's no freaking way I'm going to ever be able to solve that problem. Yes, you can cheat. You can put an IR camera. You can do some other modality. But I'm interested in the vision part of this, right? And this problem has actually 2 components to it, okay? There's a synthesis component, and then there's an analysis component, okay? In computer graphics, we often, hide things, but we do it in 2D. And I remember giving this talk at MIT, and Doral Freeman was there, and I explained that to him. I'm like, there's a synthesis problem. How do we hide objects in 3D so that they are camouflaged from different views? And he really liked that question. And, he and some of his students worked on that problem and came up with a very nice little solution for CVPR. And they were very nice enough to make me a co-author. But I was more interested in the analysis problem. And I like to keep some of these problems around, which I think of as impossible problems. Okay, I'm like, this is an impossible problem. I don't know how to solve it. I'm going to just keep talking about it to everybody I know, and keep it in the back of my mind. And one of these years we'll figure it out. Okay, so that's the editorial, on this problem. But now let's go back to you, Shyam. Can you see the octopus in this third image right here on the bottom left?
This is challenging.
All right. I'll do this one for you too. Okay, here it is. Right there. I don't know if you guys can see my cursor pretty well. You see it?
Yep.
Okay.
I think Jennifer,
this one I'm not going to help you with. The fourth one. Now you need to find the 4th octopus.
Anyone else can? I'm actually.
Yeah, anybody feel free to jump in. Shyam is feeling the heat.
Matthew.
So we have someone that says bottom left.
Yeah, bottom
I'm
left.
sorry, nope. It's not in the bottom left.
Is it a trick? Is there no octopus?
I love you for that. Okay, there is no octopus in that. Okay, you're the first people who's actually pointed it out, because the null case is really important too. If you know there's an octopus, you can keep searching, keep searching, keep searching. And when you got 1 million cases and only 5 of them have octopus in it, then that problem becomes even harder. Okay, so that's something to think about as well. And now, like I said, I used to think of this as an impossible problem. I used to show it around to everybody. I had this friend show up, Lakshman Prasad. He works at Lawrence Livermore. And he's like, I really like this problem. Can we work on this? I'm like, sure. And he came to Woods Hole. And in a month, believe it or not, he solved this problem. I helped him. It was his call. It's very, very beautiful. Okay. So I'm going to show you his solution now. Okay. Here's another example. We can actually find the octopus in all 3 of those images. I'm using this image as an example. You can see the octopus right here in the middle, right? You can see its arms and its eyes. Everybody see that? Yes? Okay. And now, you do some kind of spatial and temporal, texture-based and spatial segmentation, okay? This is a good segmentation. Well, it was a good segmentation in 2003. Who knows now, right? It is a good segmentation. It doesn't really get you the answer, right? Because you still got lots of segmented areas. But then I go to the next plot, and suddenly you can see, if I go back and forth, you can see I've gotten the octopus right there, okay? And just to make your lives a little interesting, I've also left all the false positives in, which I can very easily filter out, okay? So you can see along the edges, there's lots of false positives. All right, I can't, I should be able to see people's names here. Okay, and I'm going to pick a name at random, okay? So just to make sure everybody's awake. So Karthik Desing, what do you think? What do you think Lakshman and I are doing?
Trying to score the segments or classify them.
Yeah, that's obvious, right? Thank you for mentioning that, but how? Okay, I'm going to tell you. Okay, that's an unfair question. You work on an impossible problem for a long time, and then you make fun of everybody else because they can't figure it out. But the truth is, here's what was going on. Okay, is if you look at the perimeter, all organisms have to, even if they're cold-blooded, have to try and retain heat. So it's a smoother perimeter than you see on any other thing that's a rock or a plant. Okay, and that's why you're getting all these false positives along the edges, because that smoothness constraint along the edges, allowing that thing to pop up. And so, believe it or not, this method really worked. And it's kind of cool. In some ways, it's a little bit of a trick. But the reason I love to show this is, everybody who's a student in here, I know you're working on your own research, which is probably really cool. But in the back of your mind, keep a book of 2 or 3 problems that you think of as impossible problems, okay? And show them around to people, right? Share them. First, if you can solve them, then that's great, but maybe it's not an impossible problem. Share them, and it's a great way of pushing the field forward. It's a great way of making collaborations, and it's a cool way of thinking about hard things along with things that are much more tractable.
I have a question. So when you say it works, what is the specificity and sensitivity of what is the approximate specificity and sensitivity?
So that's a very fair question. We don't have very many examples of this. We have about 20 or 30 examples that are reasonable, and this technique works reasonably well on all those examples. And the interesting issue is it works on these octopus examples much better than on the skate example. So when we look at that skate, which I thought was an easier problem, there it's buried in the sand. It doesn't stand out as much, okay? And there we can play some games with receiver operating characteristics. What's your probability of detection? What's your probability? But for the octopus, just because of various reasons, because it's not burying into the sand, it makes a lot of sense. I could give a whole talk on this. I have some examples where these are at least static scenes where this octopus is actually moving, okay? And you see these sunlight ripples on the seafloor, and it's in shallow water. And I swear to God, an octopus is doing a 3D Fourier transform in its head, okay? It's figured out, okay, there's a spatial component and there's a time component, and I'm going to go very low pass on both so that even though it's moving, it looks like it's a rock that's sitting on the bottom, okay? So there, it's a really cool thing. And again, we can talk about it at the end of the lecture if you want, okay?
Another question,
Sure,
in the
go
chat.
ahead.
Or Laurel, do you want to ask this, or should I just read it from the chat?
I can go ahead and ask it. So my question was, would the classification pick up other animals in the image as well?
So that's a great question. Yes, it does. Okay. Yes, it does. For the octopus pictures that we have, because they were taken by a diver, they're mostly just an octopus sitting around, either on a rock or on other things. It will do that. Well, we can tweak it a little bit. A lot of times, if it's on a flat seafloor, it's easier to see. What I showed were like the really, really hard examples of it. Okay, where it's a very rocky coral reef kind of domain, which makes it very difficult. But even on a flatter sedimentary bottom with rocks and stuff, it's very, very efficient at hiding. And then there's this thing called the cuttlefish. And like I said, maybe we can take this offline after the talk. And the cuttlefish has chromatophores on its skin, and it can match the background. And Roger Hamlin and other folks are very good at raising cuttlefish in the lab. And then we can play also, and they're smaller and they're easier to deal with. They're like 3 or 4 inches. So we used to put them in these tanks, and we used to change the bottom on them from a rocky to a sandy, and it would react in real time to those changes. And then there's a beautiful picture of, we put a chessboard bottom, not calibration, computer vision calibration target, and it tried to put squares on its back. Okay, so these things are amazing, and in the wild, right? Okay, I'm going to come back to this, and again, like I said, that was an interesting digression, okay, for camouflage. But I'm really more interested in the big picture as well. What do we do with counting fish, right? Like I said, we can drive and we can take pictures. There's a problem with that. And the problem is fish behave like people do in front of a television camera. Okay, so what happens is, there's three kinds of people, and three kinds of people behavior in front of a television camera. Okay, one is, oh, television camera, I don't want to be on TV, and they walk away as fast as they can. Okay, the second behavior is television camera, I want to be on TV, and they run towards the camera. Okay. And the third kind is, oh, television camera, so what, big deal. And, and this has significant issues when we're trying to systematically count fish on the seafloor, because if they come towards you, we call that attraction. We'll tend to overcount them. If they run away from you, we call that avoidance, and they'll, will wind up undercounting. And what we want is people to be completely unaware of us. Right. And so that's, so that's another thing we've been really interested in doing. What are the effects of vehicle noise, whether it's acoustic noise, a pressure wave of a ship going by, whether it's a light, how does it affect the different species? And the answer is complicated. It affects different species different ways, different vehicles have different noise characteristics, and we have to start worrying about things like that in order to really make a difference. Okay. So, and then of course, what's happened over the last 20 years from 2003 to now is, we built these robots, people have gone out, they've gone out and really started collecting lots of data. And, we've gone from being data poor to data rich, but we're still information poor. And, and we're doing a fantastic job with machine learning, right? In whichever sphere you look at it. But machine learning underwater is we're still struggling with it a little bit, okay? A great example is, and this is a question of crossing domains, right? A lot of the people who work on machine learning would like a labeled data set. If you go to Mechanical Turk, you can get labeled data sets if you're interested in cats and dogs and ordinary things that people see. But the fisheries biologists they don't want it to just say fish or sponge. They want it to say Sebastius, blah, 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 a rockfish, okay? So they want it down to the species level. And we may not have enough examples. And we have all these issues with imaging underwater. So that's kind of an open problem. On the flip side, one of the expeditions we did, which I'm not going to really talk about, is we went out to look at some penguins with some drones. We thought there were going to be about 10,000 of them, and we found 1.5 million. Okay. And we did some very nice, standard state-of-the-art 3D structure of motion, made some orthomosaics, did the whole 9 yards, right? And then the biologists sat down and counted all the penguins by hand, because that's their protocol. Now, here's a number for you. If you count from 1 to 1 million at the rate of 1 number a second, it's going to take you 11 days nonstop. Okay. Now, they had 1.5 million penguins there, 750,000 pairs. Okay. And they wanted to count it 4 different ways. Okay. They wanted 4 independent counts of it. And there are errors, because depending on how you count them, and they try very hard, but that was what they were going to do. Now, the student of mine who went there said, this is crazy. I'm going to do a CNN on this, and I'm sure it's just going to work. And on penguins, it worked really well. Okay. And we were well within, the error bar that we had with the individual counters. But there, because we had people individually counting them, we could get some nice training data, and the data is very consistent, and it was easy to do. And so there's certain things that it works with, other things maybe not as well. And so that's kind of interesting. Okay, I'm going to move a little bit and talk a little bit about bipolar robots. And, we like to say we're bipolar. We go to both the Arctic and the Antarctic. It's, it's one of the most beautiful places to go in the world. If you ever get a chance to go to Greenland, or the Arctic, or the Antarctic, grab it with both hands. do not, drop everything. If I wasn't married, I would go live there permanently. Okay. And so it's been wonderful. So I'm going to talk you through some of the things we've been doing over there. And we've, in the last, I stopped this slide at 2018, but in the last 10 or 12 years, we've done dozens of cruises there. Okay. And so the basic idea there is we're in an ice-covered ocean, right? And people really want to make measurements under that ice, right? I'll show you some examples. In 2007, we found 4 mountains on the seafloor, which people didn't know about. Okay, that's kind of mind-blowing in lots of ways because they were hidden under the ice and you couldn't really quite see them. There was a series of what people thought were earthquakes in 1999. Turned out it was a volcanic eruption. All right, and so here's the basic idea when we're going there. We build a robot. We drive an icebreaker, which costs a lot of money and it takes a lot of time, to a spot in the ocean. We make a little hole. We drop the robot in there. It dives to 4,100 meters. When we did that, that was the deepest any AUV had ever been. And since then, of course, we've done much more, right? We go to 4,100 meters. We do a survey. It takes us about 18 hours. We come back. In those 18 hours, the ice is not static. The ice is drifted about 10 kilometers. So a helicopter takes off from the icebreaker, tries to find an open hole in the ice or lead in the ice, somewhere close to where we think the vehicle is going to come up. We drive the icebreaker to that. Then we talk via acoustics. We don't have Wi-Fi. We don't have any RF communications to the vehicle, and we guide it to that hole. What can go wrong? Okay. And this brings me to the second law of robotics, which I'm going to talk about in just a second.
So we have a question on the chat, which is, how do you decide which spots in the ocean are interesting?
So, that's actually a really good question. So, we're always working with, in this case, I was working with, a geologist. Okay. I have a friend, his name is Rob Stone. I got to know him and he came and he said, you know what? I want to there's a big hole in the world's seismic network under the Arctic Ocean. I want to put a seismometer underneath there. Okay. Can we make, and he had these ideas of how we would do that with an AUV. Okay. And then what I haven't told you is that it took us 10 years to actually get it funded. Everybody would say, this is way too hard, way too hard, way too hard. Okay. And actually got funded by Astrobiology as an analog for Europa. Okay. And I remember what the program manager said is she said, you cannot cheat. Okay. When you're trying to go down there, because we were looking for hydrothermal vents under the ice, signs of life, which are very, very basic under the ice. Okay. And I'll get to that in a second. So usually what it is, and you'll see this in some of the other expeditions, right? We have some technologies, we have some ideas, but we're always talking to people. And then the people will say, hey, can you do this for fisheries? Can you do this for this geology work? Can you do this for sea ice? Can you do it for penguins? And then we'll work with them. And then when that happens, we'll see new applications of our technology that they didn't dream of. And that's the beautiful back and forth that goes along in a lot of the work that we do. So here's an example of when things didn't go very well. We knew that the vehicle was there somewhere, but the hole had closed in on us. We tried to find it. We knew it was within 100 meters. But if we brought it up under the ice, the multipath under ice is so bad, we would have lost it within 100 meters of each other. Okay. And eventually we couldn't do anything. We said, all right, bring it up somewhere there. And if you see my cursor, we could barely just see it right here, this little yellow dot. And luckily we saw that yellow dot and we could recover the vehicle. But now here's the cool stuff. What did we find? Okay. One of the things we found underneath was these, we didn't find a hydrothermal vent, which would have been very cool, but we found these microbial mats. We had another instrument there, which went and sampled them. And then we found 13 new species very high up on the evolutionary tree, which were in this microbial mat. So it was kind of cool, and then there was a Nature paper on the explosive volcanism that took place because we could actually see evidence of that as well. Okay, and so this gets me to the other point I want to make, right? Here's another great example. This was Ryan Eustace's work when he was one of my students. Of course, now he's a professor in his own right and doing all sorts of things, like being the vice president of Toyota for autonomous cars. But we went out and I was part of the lab. This was way before I was even a student there. Bob Ballard had found the Titanic. He founded the lab. He was going back there and wanted to make a mosaic of the whole thing. We agreed to do that. And when we collected that, I was like, this would be a great example for doing SLAM underwater. Okay, we wanted to really try and see if we can push that. And the state of the art at that point was Sebastian Thrun had come up with this new concept of information filtering. Okay, but he had, it was an approximation. Okay, and again, this is way back, God, when would this be? 2000s, early 2000s. And this was 866 images. And, you know, given what we had for computation and where we were with about 800, you know, more than 500 images, the information filter approximation would blow up. We just couldn't keep it together for SLAM. And what Ryan said is, why don't I try and see if I can come up with analytical expression for information filters? And that's, what he wound up doing. And it was all driven by the fact that he wanted to map out the Titanic. And so that's, and of course he got, best paper award at ICRA and stuff like that for that. And what I want to point out is that, when we went out to map the Titanic, we weren't thinking about, how it would change the analytical framework for information filters. But we were driven to that by the fact that everything that we had didn't quite work. Okay, so that's something to keep in mind as well, right? And so now here's what we do nowadays. We started moving. This is another expedition. This is in the Antarctic. One of my students and one of my postdocs working with the Australians, and they're drilling a hole so that they can put some navigation transponders.
All right, I'll count it down. 3, 2, 1, mark. Okay, transponder A is at south 65 degrees, 08 decimal 05.
And because we were going shallow in this case, usually we don't get good pictures of our roadbacks because we're too deep. We put a little GoPro on the vehicle, and as you'll see, there was this little ROV there as well, which I got to see what we were doing. And what we're doing here is we're trying to map the underside of sea ice, and sea ice is moving. So when you do SLAM, mostly we're doing SLAM on static environments. And here we were transitioning to what we call quasi-dynamic environments. The ice flow was moving. It was both translating and rotating. It was relatively slow, a couple of meters per second, and up to 10 degrees an hour. So it's slow, and we could use consistency in the microbathymetric mapping to actually come up with a SLAM solution so that we could actually map and look at certain 2D features of the ice flow. The old way of mapping the thickness of the ice was to go in there with a drill and make a hole and then put a string with a weight at the end of it and try and measure how thick the ice was. And that had all sorts of interesting problems with it.
So Hanu, Subesha has a question.
Sure, go ahead.
Well, that's an amazing picture, by the way, the last picture you had.
Oh yeah. That made the cover of lots of magazines, right? Where is it? It's right here, and we have only so much time. Right.
Yeah.
Yeah.
Professor, I was wondering if
shoot.
Yeah, I was wondering if there was camouflage detection done in the marine organisms found under the Arctic Sea, but I'm just curious if camouflage
in the Arctic, so we weren't really looking at marine, not in this cruise, we weren't looking at marine organisms. We had another cruise where I have a paper which is called The Fishes, I'm a co-author, okay, which is called Fishes of the Western Antarctic, okay. I'm actually, maybe I'll talk about that in a second. So out here, though, we were looking at sea ice. We're trying to understand what is the roughness of the underside of the sea ice for lots of interesting reasons. Okay. And so if I scroll past this, what we've got is, let me see if it goes up here, right here, about here, right? Yeah, so we're making a map of the underside of the sea ice. Okay, and actually the next slide just shows it. Okay, so what people are very interested in doing is saying, okay, what's the top look like? How much snow is there? And then what's the ice draft, or what's the bottom look like? And getting, they call it the 3-layer cake, getting a strong understanding of everything right there. Because the top we can always look at with satellites. And we have certain instruments and we have certain things we can say about the bottom. But that's a relationship that they're still trying to tease out. And again, this is in 2012, okay? So I do want to show you one other thing, and which is I want to talk a little bit about the second law of field robotics, right? I've shown you all this amazing imagery. We go out and we're just having so much fun, and everything is hunky-dory, right? The reality is kind of different, okay? We have a saying, somebody puts up data and say, okay, this is typical data. What they really mean is it's the best data we ever collected once in our lives, okay? And now when we're doing field robotics, I talked about the first law, which is, the number of deployments should equal the number of recoveries. There's a second law. And the second law says, if you're following the first law, to a T, you aren't pushing the limit enough, okay? And so here's some examples of when stuff goes wrong, okay? And we want to share this with you too. Here's one thing that happened. I'm going to just talk over this video.
White one is the third one, right?
We launched the vehicle, and we had done all sorts of practices in back home in regular water, and we forgot to turn off one of the software switches, okay? And the vehicle got stuck under the ice. And so you can see the vehicle is actually pretty big. It's 1.5 meters, right? It's about 1 meter high, and the ice height is easily 1 meter. And there it is, stuck in ice, and there's nothing we could do about it. Right next to the ship, literally 10 meters from the ship. And one of my students rigged this little hook in the workshop. We had a little ROV, and which is a real, in those days, it was a pain to drive these things, okay? They were very squirrely. And now our first dive out, we had a vehicle stuck, and we would have lost it if not for, Jeff right here and Chris Murphy, who were the two people who were responsible for getting it out of there.
We have a couple of questions in the chat about, I think 2 people have asked, how does the water temperature affect the performance, or do you have to do anything special to make them operate in really cold water?
Great question. So actually the water is our friend usually, okay? Because the water never goes below 4 degrees. I mean, sometimes it's very close between 0 and 4. Here's another example where we got the vehicle stuck under ice. We used, I'll answer that question in a second, okay? We had to use avalanche beacons, which skiers use. We had one on the vehicle. We went out and searched for it on the ice. And then here we are, that's me and my students digging a hole in the ice so that we can attach a line to it and pull it out. And we're doing this in the middle of the night. I mean, of course, it's daylight all the time. And the captain of the icebreaker who's responsible for us is pretty unhappy with us at this point, because we're like 700 meters away from the icebreaker in the middle of nowhere in Antarctica. Okay, and so coming back to your question, it actually gets really cold in air, and our bigger problem is the air temperature, right? And connectors get really, really cold. We worked in Greenland where the temperature, and I won't talk about that in this talk, where the temperature was -30, -40. And it doesn't matter when you're talking whether it's Celsius or Fahrenheit, because they're kind of equivalent. That's cold. That's really significantly cold. If you use a laptop, if you pull out a laptop at -40, within a minute, it's dead, okay? And it won't revive because the lithium-ion battery is gone, okay? You have to take it back, and if you're lucky, you warm it up, and it takes several hours. And so what we would do is, a lithium-ion battery for an aerial vehicle, for instance, for a drone, we would keep them warm next to our skin, okay? We would use our body temperature to warm them. And then we would pull them out at the last moment. Now, the really good thing is there's a little bit of internal resistance in these batteries. That's a bad thing for battery capacity. It's a good thing for cold, because that internal resistance heats up the battery, okay? It's I squared R. And so what you're doing is you pop it into the drone, and you make sure you turn the drone on really, really fast and start spinning the props, so you're drawing reasonable amounts of current. Otherwise, the battery's going to die on you. So there's all sorts of interesting issues. Here's another one. When we were, one of my friends, this is not me, one of my friends was deploying an instrument on the ice, and our underwater cables are usually black. And what he realized is in April, you have 24 hours of sunlight in Greenland. Even though it's -30, the sun heats up the black cables enough so that they start melting through the ice, and your whole instrument basically melts through the ice and is lost. Okay, so what did he have to do? He had to put, white cover, white tape over all his cables so that they didn't absorb sunlight. So there are all these little gotchas that happen, okay? And, and I should move on. We got lots of coverage. And the one point I want to make is, it's always nice to be in the newspapers or on TV. Your mom loves that. She makes clippings and sends it to all their relatives. But, there's all sorts of interesting things that happen. So my favorite headline of our coverage was penguin-powered robot finds Antarctic sea ice is thicker than first thought, okay? I don't know where they got that from. We did find sea ice was thicker. It had nothing to do with penguins, but that's the nature of the beast. Okay, I'm going to move on a little bit and talk about another vehicle we have, a surface vehicle. Okay, and this is something called the JetJack. And what was interesting is, I always want to work with surface vehicles. I didn't want to build one per se. The problem with all the small surface vehicles that exist, they look like kayaks. And they are really kayaks that you modify. And people would run them with lithium-ion batteries, and they normally did not have enough oomph to really work where you wanted them to work, which is in the coastal ocean, right? And in the coastal ocean, what happens is you get lots of currents. So a lithium-powered kayak can't handle 6 to 10 knots, which is 3 to 5 meters per second of current. And then, I was working with this friend, Peter Trakowski, and another friend, Rocky Guy, both of them are scientists. And Rocky said, hey, I just found this kayak. It's got a Subaru lawnmower engine on it, and it can do 15 knots. And it only costs I think it was at that time, it was like $6,000. I'm like, perfect, let's buy one. We're going to take a Pixar, we're going to pop it right in there, and we're going to make it autonomous. And we can do that in 2 weeks. And they both laughed at me, right? And we did actually manage to do it in like 3 weeks, okay? And now suddenly we had this powerful platform that we could use. And one of my other friends had always said, I want to make measurements right at the edge of a glacier, okay? A calving glacier in Greenland, because nobody really understands what's going on right there. And I want to make these measurements. And, it's not calving all the time, but there's a finite probability that a large chunk of ice is going to fall off at any time. And so you don't want to be there in a small boat because you don't want to die, okay, for those measurements. And so he said, yeah, why don't we use this? It's relatively cheap. And we can get very close to the glacier and we can make these measurements. And hopefully, a big chunk of ice doesn't fall on it. If it does, nobody's going to get hurt. Okay. So we went out and there's a nice little story there. If you look at this big picture, it's taken from a helicopter. There are a couple of stories there. I'm going to be running out of time soon, but I'll tell you this one. The helicopter pilot basically goes and puts us out on a camp next to the glacier, and then we go and make our measurements, right? And the helicopter pilot is your support. If someone gets hurt, that person's going to have to come in and get you out. That person is really responsible for you. And if the weather goes bad and someone's hurt, that's, again, the helicopter pilot is going to try really hard to make sure things happen. And so he's coming in and he sees the JetJack, which is right there next to the glacier, and we're in this small boat right there. And he starts screaming on the radio, there's someone very close to the glacier, get away from there, that's dangerous, don't go there. And we're like, and there's a lot of noise if you've ever been on a helicopter. It's a lot of noise, it's a noisy environment. And we're trying to tell him on the radio, which is another noisy environment, no, there's nobody there, it's okay. And he's screaming, I can see it, you guys are, don't lie to me, I can see it, tell that to come back, right? And he lands and he's furious, he walks out and he sees this thing and he's like, oh, that's kind of cool. Okay, so sometimes it was interesting. Anyway, we did that. We got some very nice data. That was, and we've gone back, and I'm going to talk about what we did when we went back again with Fiamma Strano and my collaborators there. Now we've got an autonomous JetJack. What can we do with it? Hey, we're robotics people. You have an autonomous car. We can have an autonomous ship. Actually, it turns out the Norwegians now have an autonomous ferry, which goes back and forth. And there are certain rules of the road, just like they are on the road. And this is work done by James Meyer and Zizi Yong, two of my, Ziyong Zhang, sorry, Zizi, two of my grad students, and in making this autonomous. And I'm not going to really talk about it, except for, just show you this video. This is the Charles River in Boston. Green is the JetJack. The red is us. And all this is being done autonomously by the JetJack. All this tracking, it has a radar on board. It has an electronic chart. Those colors show when it has to avoid us because of the rules of the road. And we've speeded this up quite a bit, but it blew us away how well it worked in terms of replanning its task as it moved down the river. Okay, and this goes on, and it was kind of interesting at the end. We did this in the winter, and just because that way it was cold. No, I'm just kidding, because that was the time somebody had to finish the thesis. But the river was kind of empty, and so that was perfect in some ways. And suddenly we saw these 3 boats come on, and we put the JetJack in a hover mode, but it still did a really nice job right here in terms of avoiding us and those other other boats. And here it is, back. Oh no, not this time. Next time around it'll go back. But you get the idea. So this is kind of cool, and we've been doing that. Okay, I'm going to move on a little bit more, and now I want to talk about mapping icebergs. It turns out in Greenland, all these icebergs fall off, and we don't really have a good handle on how much fresh water these icebergs are bringing into the world's oceans. Okay, we're off by maybe 100% in our estimates. And I'm not doing the estimates, but these are my friends, Fiamma and Dave Sutherland and Claudia Enides. And these are the people that we had gone to and looking at the glacier. And so we went back to map icebergs. And one of the problems is, again, with SLAM, everybody assumes it's a static world. Here we have a quasi-dynamic world. As we are mapping this iceberg, it's moving. And so, this little schematic that Vikrant Shah, one of my students, made shows that, there's a huge distortion, and this is a little exaggerated, in the measured shape because something moves. And what we really want to do is get a map of the iceberg that's in a frame that's anchored to the iceberg as opposed to the world frame. Okay, and one of the things we could do is, hey, let's see, we can do structure from motion. Let's do a 3D structure from motion solution that will also give us a navigation solution. We can use that for the multi-beam underneath, which is hidden, which they're also very interested in mapping. And then that way we get a total volume for the iceberg. And then doing that repeatedly, we can see what melt rate is. And there's some, very interesting issues there. One of them is, of course, low contrast environments. And I have to make this editorial comment here, right? When I moved to Northeastern, I started working on things other than underwater, and and had all these great ideas. And then I had this saying, it was like, God damn it! Whenever I get a good idea, someone in ETH, EPFL, or MIT has already done it. Okay, and then we saw this talk by one of those people, and it's true. And the few places where we still have lots of problems with computer vision are underwater, ice, and snow, basically low contrast environments. And so that's why this is kind of an interesting little problem. This is a cool little thesis, that Vikrant's done, and we've, mapped up multiple icebergs. We can get the bottom and the top both, lined up, and we can make sure that they're scaled correctly. And then we can actually now, anybody can make a map, right? That's one of the issues. But now we can make maps that we have some error bars on, so that when we compare them over time, we can see how much mass loss, how much melt rate there is. And that's what's kind of cool. And here's another view of that whole thing. Okay, and here's the volume differences. So this is kind of cool. This is still unpublished work, but I'm really excited about it. Okay, the last topic I want to talk about is this. Right now, you look at SLAM. SLAM's been around for a long period of time, and we have these beautiful data sets, whether it's the Kitty data set, whether it's the Victoria Park data set on land that people have spent lots and lots of time working on. Okay. Now, as soon as when you look at that picture on the left with 3 people in it, right? As soon as we try and do a SLAM solution with that kind of density of people in the scene that are moving, SLAM breaks down, okay? It just cannot handle dynamic objects very well. What winds up happening is people tend to wear clothes that are bright. You look at all our favorite feature detectors, and they'll pick up the features on the people move, and now you've got something that's inconsistent, and all hell breaks loose. Okay, now we're not the only people who follow this problem. This is a front-end problem, right? SLAM has also worked really hard on the back end in terms of loop closures and stuff like that. But on the front end, a little less work has been done. And there are some people who have, what's the classical way of handling this problem? One classical way is say, hey, I know how to segment the people out, right? I can use machine learning to segment people out. And then I'm going to in-paint something behind them. And if I have an initial map without the people, and I know roughly where I am, then I can in-paint behind what these people are. Problem is, that's an in-painting problem. You have to initialize everything, and you still can't use those in-painted features as features within your SLAM map. Okay, so we decided to take a slightly different view. This is work that's being done right now by Pushami Kawiti, and we decided to look at light fields. Okay, now I'm hoping some of you know what light fields are. I'm going to give a 20-second introduction to them. Okay, so you have a bunch of cameras. Usually they're a 2D array, and for various reasons, we are robotics people. We went with a 1D linear array of 5 cameras. Okay, so when you have a point in space and XYZ, we have multiple rays which are looking at it, and those rays all combine, and we can play games with, because we have very good extrinsic and intrinsic calibration of these cameras. We have ways of sorting those rays out and combining them in interesting ways. Okay, and people use these, and we have these cameras from Lytro, for instance, and other companies where they're lensless baits. Our cameras are not lensless baits because we, as roboticists, need a wide baseline. If you're a graphics person and you're very interested in this problem, then a lenslet based camera makes a lot of sense. But if you're interested in the following problem, let's say you have a person, and you can segment that person, that you can see that person in 2 views, but you can see behind that person in the other 3 views, right? And the way we can do this is by having a reasonable baseline in our cameras, right? So what we want to be able to do is say, okay, we're going to segment this person, and we're going to figure out which rays from which cameras are intersecting that, get rid of those rays, and then find the other rays in the background behind that person that we can then use to reconstruct, the image. Okay, and what do we need? We need to do all sorts of things, and I will not go into the map. Pushami has a paper up on archive. You can look at it. Okay, we need to do semantic segmentation to figure out the objects that we think are dynamic, and then we need a depth map behind them, and then we need to know which cameras and which rays to use to actually pull and reconstruct that. Okay, now this all sounds good. Let's just show you something. Okay, so here's the example, right? This is a static example still. On the left is a frame, then there are 5 frames really, and you can segment out the people, you can do some depth estimation, and then you can refocus past those people, okay? And you're doing, we're doing as good a job as the segmentation. You can actually kind of see some shadows if you look carefully, and you can also see the shadows of the people, okay? But what we've, refocused this image on is real. It exists in the physical world, and we can use that for a SLAM solution, okay? So here's a movie of this, okay? This is Pushami, a real-time, original image, dynamic, static. And then, of course, so we can do this reconstruction. And let's now look at how we do it. So this is our setup, 5 cameras, Alienware laptop, and we're going to do a little loop, and we're going to run 3 different, sound algorithms. ARP-SLAM, DynaSLAM, which has RGBD as well as, it's got the depth as well as that. And then what we see is very quickly, ARP-SLAM mono fails because it doesn't initialize properly. DynaSLAM works for a little bit, and then it loses it just with this kind of errors. And you can see, we're doing this in real time. This is a real time, video. And we can filter past the people. And essentially we can do loop closure, and we're doing a really nice job on the front end. Okay, so I'm going to end it there, and and I'd be happy to take any questions. And before I end, of course, I'd like to thank all my students and my collaborators. My students do all the work. I get to just talk about it in interesting ways. They're absolutely fantastic. They go out to Antarctica, get completely soaked like that Vikrant there, and then sometimes we go to Antarctica and we jump for joy as well. But it's always fun. So thank you so much. I'd be happy to take any questions you have.
Thank you so much, Hanu. This has been a very fascinating talk. I will start off with a couple of questions. You start off the talk by saying that, I know that you started off the talk by saying that don't build new robots. But a lot of the thing which at least came across to me in this talk was, it's a lot of human effort to basically deploy this robot for, I'm assuming, a couple of hours, and just like it's extremely expensive. So as you look into the next decade, do you think of smaller, cheaper things which you can basically deploy, which have, because it seems like under icebergs and stuff, you wouldn't have so much waves. I'm assuming that there are not too many waves that they can have a little bit of locomotion without sophisticated control and so on. Do you think these getting miniaturized a lot more? And what are your thoughts on the future of this?
So that's actually a really good question, right, Shyam? So, I want to build the smallest vehicle I can. Okay. So one of the things I didn't tell you is we were having this discussion yesterday at a different conferences. When we built Seabed, one of the constraints we had on it was what is the biggest shipping container that FedEx will send anywhere in the world? Okay. Because if you build bigger than that, you have to send it in a 18-foot container. And that takes months and costs a lot of money. So size, weight, power are all constraints we want. Now, what winds up happening is as the ocean is a harsh environment. You have to bring your own navigation. You have to bring your own lights. You have to bring your own autonomy. So I would love to be able to say I can throw out something which is, the size of my fist. It's not going to work. Okay. I would love to be able to say we're going to miniaturize them like we have the drones in air, but what are those guys using? They have GPS. They have, they have the sun. So, and and the other big issue is you have to, you have to deal with vacuum, right? Because just like with space, we have vacuum, all our internals have vacuum. So we have to keep the seawater out. They're keeping the vacuum out and the air in. We're keeping the water out and the air in. Okay. So we have to deal with that. And anytime you put metal, you have to also float it. So what we don't talk about is the syntactic foam and the flotation that's required for any sensor that's heavier than water, including our batteries. So, it's if this was a marine robotics group, I have this great slide which shows what happens to the size of the vehicle as a function of depth. Okay, at 100 meters, what does it weigh? It's man-portable. At 2,000 meters, it's not man-portable. It's about 300 kgs. At 4,500 meters, it's 400, 500 kgs. At 11 kilometers, now it's weighing a ton. Okay. Now the cable that goes down to that ROV weighs more than the vehicle. The drag on that cable is so much that cable breaks. So there are all these issues that we haven't talked about, which come into play. Now, and then the other thing is complexity, right? We're all looking at, hey, let's get swarms of vehicles and let's get them all working. There's a significant amount of complexity in just working with one vehicle. And getting 2 going is okay. Getting 4 going, it's a hard push. So, I hate to say this, but I'll put this out as a challenge. All those people who've been working on swarms, they've been working on swarms with little robots inside, rooms on a 2D plane. Let's get you out in the real world. And the real world slaps you in the face a lot of times, right? And so they are doing good work in terms of algorithmic development, right? In terms of using those vehicles in those kinds of environment. But when we get out in the real world, there are all these other issues that come into play that matter as well.
Following on Professor Shyam's question, I was wondering if, since you spoke about vacuum and other issues at deeper water level, there has been a lot of research about trying to mimic the movement of seahorses for actuation and bioprinting octopus skins. Now, these kind of greatly reduce the thrust because of vacuum and the buoyant effects. They kind of nullify those, and they're significantly smaller machines. And the production cost can also be scaled down. So even if we lose a couple of these robots, it's fine, so long as the information in them can be transmitted.
Yeah. So you're right, Suresh. There's a whole host of work being done on biomimicry, and what I would say is right now it's cool work. Right now it's not ready for prime time. There's a big difference in demonstrating something that kind of sort of works and maybe works in a pool versus taking it out in the real ocean. Okay, we had, God, I can't mention this. This is getting recorded. It's going to be all over the internet. We have lots of examples of people, making claims and then going out. And here's the real saying, right, which we use a lot. The ocean is not cruel, okay, but it is unforgiving, okay? And so it's a harsh world. And, and I can say that too. Remember the second law? I've lost an AUV, okay? We have the AUV conference when nobody wants to admit that they've lost a, $500,000 or $750,000 vehicle, or heaven help us, a $10 million vehicle. And then we'll sit there and we'll say, there's no microphones. Everybody gets a coffee or a drink, and we tell each other stories of all the bad things that have happened to us. so that we can learn from each other's mistakes. And so, like I said, it's a harsh world. And I think the whole concept of bio-inspired robotics is good. You know, when I was a grad student, one of my fellow grad students made this, you know, fish propulsion robot, and it was amazing in lots of ways. But again, you know, we still have work to do in that area.
We have a couple of more questions. I'm going to basically go over a couple of them. Astitva had a question about communication. Like some of the videos you showed, there was lots of.
You were breaking up there, Shyam.
Anu, are you there?
Yes.
Oh, perfect. So we were talking about the communication aspect of underwater. In a lot of the videos, we saw a lot of sound when you were playing the robot. Does it interfere? And also, can you talk more broadly about the challenges of communication, given that it's limited bandwidth and so on?
And
the application.
So you know, there's a whole host of people who work on underwater communications. Okay, and you know, here's what's happening. There's you know, when we think about a signal that's being sent out, right? It's usually when we think, let's assume we're talking about the Mars rover. The big issue we have there is we have limited bandwidth and we have a delay. Okay, but that bandwidth is basically constant. We know what the channel is. The channel doesn't change very much. When we are underwater and using acoustics, not only does you know, not only are we limited in our bandwidth, but we are also limited in terms of the channel's characteristics are changing all the time. So we're trying to understand the channel's characteristics. We, you know, by what's the dilation and the modulation, what's happening in the channel at all times. We have to do it's a channel estimation problem as well as an acoustic communications problem. Okay, and the vertical channel is easier. You know, the horizontal channel is much worse. You know, typically when we're running our robots, we're receiving, what would I say? I would say 30 bytes a minute. Okay, that's all we have. Okay, so we have some students who worked on what can we do with that 30 bytes. Okay, and you know, even when you, and that's another target, even if you look at JPEG compression, JPEG 2000, under 256 bytes, you're dead. Okay, under 2K, 4K, you're really hurting. So we wound up, you know, people have wound up making their own compression schemes. You know, you don't want to reinvent a wheel if it exists. Lots of people have worked on compression, but this ultra compression that we need to work on is different. Okay, the transponders that we use are big. You know, so there's all these, and then the noise characteristics of our vehicles really matter as well. So there's all sorts of interesting issues with acoustic communications, and then we also use acoustics for navigation. You know, we have beacons which send out a ping and come back, and how we deal with that. So that's a whole different talk, and we should get into it some other time too. Yeah.
Yeah, another question from Alex about underwater GPS. We had a talk earlier this week on creating acoustic sensors attached and trying to localize the things. So similar to the satellites which are deployed by the military back in the day, are there any efforts you know of where people want to create GPS?
Sure. So, you know, here's the classical way of doing it, right? So one of the issues with sound underwater is that it propagates as a function of frequency. So if you're at 1 or 2 hertz, you can send a signal. And there was this very famous experiment called the Heard Island experiment, where you could send a signal from Heard Island in the Indian Ocean and it was heard all around the world. And they were using, you know, acoustic tomography to figure out how the Earth's waters were changing when, you know, when people were really worried about quantifying temperature change because of global warming. Okay, so now let's move up in frequency. If you're at, you know, if you go into a doctor's office and get an ultrasound, you're at 1 or 2 or 3 megahertz. Okay, and now if you want to do imaging, you're at a few and you're at a few 100 kilohertz. You get ranges of about 100 meters. Okay, and so we can use those. If you want to do navigation, depending upon what your application is, we'll use different transponders. We might work in, say, at 10 kilohertz, where we'll get roughly 10 kilometers of range. Okay, and then there are interesting issues about how do you want to code up those signals. Okay, the other interesting issue is, you know, when you look at GPS satellites, they rely on timing. Now, the good news for timing is, you know, GPS satellites need timing for the speed of sound, right? We're worried about acoustics, and the speed of acoustics is way, way, way lower, right? But you still, if you look at, you know, the atomic clocks, the chip atomic clocks that are available on chips right now, right? You're still looking at drift rates where you can't last more than a few months without incurring errors of the orders of few meters. Now, some robots need a navigation good to, a few meters. Others don't care. They'd be happy with 100 meters. So then they can use dead reckoning. So there's a whole host of solutions. And, it's a problem that's been looked at for a long period of time. And there's lots of ways of solving that problem. Yeah.
So I'm going to combine one question from Ian and Shao about energy. And the question which Ian has is, have you thought about resident AUVs where you don't have to go there, you don't have to have a human, but it just stays there, you can recharge it? And Shao was talking about something more futuristic, which is, can you install charging stations underwater to keep them from charging themselves and continue to collect the data?
So, funny you should say that. At the University of Washington is something called the Neptune Observatory, okay? And what they've done is taken a fiber optic cable. It goes off the coast of Oregon, goes a few hundred kilometers to a site that's of very strong interest to people. And so now they have a little station that sits on the sea floor where you have a fiber optic cable going to it, so you can get lots of data back. You can put cameras up there and you have power. And then you could have a resident AUV sitting just like they said, and going out doing missions and doing stuff like that. So that's definitely on the cards. It's not a solved problem as yet. It's one of those problems that keeps coming up. When I was a postdoc, that's what I worked on. I worked on something called the Autonomous Ocean Sampling Networks, where we were going to put out these robots. We're going to have acoustic comms with them. They would have a big battery in charge. And we made progress, but we never delivered. And now, same thing happened like 10 years ago. And now there's another push. Again, we call that docking underwater, and where we're working on that.
I'll ask one last question before we let you go. It is from Ethan. Given the large costs of these experiments, how do you balance between your first and second loss? That is, how do you strike the balance between being too ambitious or not being too ambitious enough? And do you have any rules of thumb about that?
So, that's a really good question. I think, you look at the costs of doing these operations, right? And ships costs are high, icebreaker costs are even high, but independent of the cost, there's also this other thing called opportunity cost, right? So, the National Science Foundation may fund, 100 days of icebreaker time for a year, right? And they have the funding for that, and it costs a lot of money. But if you get 40 days of that, that's 40 days that some other science party didn't get. Okay, so we have this whole ethos and we have this whole culture that when we get ship time, we work our asses off. We're working 24 hours a day. There's 3 shifts. Different people are working so that we can really get a lot of work done. So typically, what I haven't talked about is, when we go out with the AUV on a ship, there's other people who are doing, other experiments, a CTD. So if I'm working 8 hours a day, it might be broken up into 4 or 5 different segments. And somebody else, I deploy my vehicle, it's off, and I know it's going to work for a day. During that day, the ship is now taken over by someone who's, say, a chemist and who is doing water sampling. The ship might be taken over after they've done by a biologist who's sampling or trying to get. So there's a whole host of things that are going on. And then when you talk about the first and the second laws, right? It's entirely a question of priorities, right? Here's a number which is actually kind of staggering, which we love to put up, right? Before we shut down the space shuttles, each space shuttle launch cost, and the answer is $500 million. And that did not include the cost of the shuttle. Is that worth it? Is anything we do, is any proposal that we get from the National Science Foundation worth it? And that's something that's determined by a lot of factors. What does society think? And some of those factors may be wrong, right? For instance, a great example is marine archaeology. I didn't really talk about that. Marine archaeology, those people don't have money. They would love to, take the tools that we have and use them for marine archaeology. Is that important? I think it's important, but it's not a science question, so it doesn't get funded by the National Science Foundation. The marine archaeologists I work with, some of them are, reasonably wealthy. Others, I know one who goes to Europe and runs tours for 2 months, makes money off that, and then uses that to go on his own digs. Okay, in archaeology, they have a saying which says, they tell the grad students, please don't mortgage your house for archaeology. Okay, and so there are different issues, and there are different communities, and different communities have different amounts of funding. And that's unfair in some ways, but we've decided as a society, for better or for worse, and that's how that goes.
Great. Thank you so much for taking the time to talk with us. And I think it's been fascinating to know about the world of the oceans and the decades of work you all have put into doing this. And I feel like the next decade or so could actually be even more exciting. So it's really exciting to hear your thoughts.
Thank you so much. And to all of you, like I wish I was there in person. But if you're ever in Boston, stop by Northeastern. We have a very cool lab, and we'd love to show you around. And we'll look forward to seeing you all in person sometime. Take care.